Hello and welcome to our discussion of Newton's law of gravitation. And we must first recognize that there was a historical effort to define what gravity is. So the discussion of gravity continues and extends to describe to us what relativity is. But back when we were discussing classical mechanics, gravity is the center of all of these very important scientific advancements. So gravity is a force. Gravity is a force that is comprised of the mass of the object, the mass of the object multiplied by a by an acceleration that is pulling that object. And we discussed in class how space is not really empty. Space is like if you drop a bowling ball on your bed and then you drop a billiard ball, this pool ball, and then you drop a couple of marbles on your mattress, you will see that most of the marbles are going to be attracted towards the really big bowling ball. So we now going to learn that each marble is going to move closer to the center of the biggest mass based on the mass of each marble multiplied by that acceleration that is pulling each marble to the center of those really big objects. So this is Johannes Kepler, very famous German scientist, and this is Isaac Newton. And they showed how the planets move. And the Isaac Newton was able to describe the gravitational force that is causing the planets to orbit around the sun. So we have to first understand that the shape, the orbit of the planets around the sun is not a circle. It is not a circle. It is an ellipse. So an ellipse is the form that is like an egg shape around the sun. So this is the sun, and the planets move around. Each planet has its own orbit. It's rotating at its own speed, obviously, because the planets have different sizes. So they have the different gravitational force pulling them to rotate around the sun based on their respective mass. So the orbit is not a circle, so there is no radius. We cannot say that at each moment in time, there's an instantaneous displacement that is equal from the center of the sun. That is not true. The planet could be recognized in these two very important points. The first point is known as the aphelion, and the second one is the perihelion. The aphelion is, if you look at this egg and the sun is right here, the point that is closest to the sun, that is known as the aphelion. While if you look at this point that is the farthest away, the farthest point the planet can ever be in its orbit around the sun, that is known as the perihelion. So here we have an ellipse, which is a closed curve. And we learn that the sum of the distances from a point on the curve to the two foci. So we have two focuses. There's F2 and F1. And we learn that the sum of the distances from a point on a curve to the two foci is constant. So if you have a point, no matter where you move in this track, in this orbit, if you make a straight line, to connect to each focus, you will see that the distance between these two lines is the same. So for any closed orbit, little m, that is the planet that is moving around the sun, follows this elliptical path with m at one focus. So big M represents the big mass, the sun. The sun is big M, while the planet is little m. So the aphelion is the closest distance between the planet and the sun. The, the closest distance between little m and big M, that is the aphelion, while the distance between the big M, the sun, and the planet, that is the farthest, is known as the perihelion. So we can draw this path if we have two pins and we put like a rubber plastic band and we start to make a shape. You will see that this shape will be exactly an ellipse. So you can draw an ellipse as shown by putting a pin at each focus and then placing a loop of string around a pin and the pins and tracing a line on the paper. You'll get that ellipse orbit. Now this is very interesting. Here we see little m, the planet with the smaller mass versus the center of gravity. That is big M, the sun. And obviously the planet is rotating around the sun in this ellipsoid orbit. At each point, this planet obviously has an instantaneous velocity. So here it's pointing in this direction. Here is not going to be pointing in the same direction. It's going to be pointing at this direction. So there's always an instantaneous there's an instantaneous vector. There's an instantaneous vector of velocity that is pointing to us at which direction is this planet moving with that speed at which it's moving at. So here we learn that the shaded region have equal masses. So for example, this is the center, M. If you make a line, like let's say the planet now has arrived to point A, then traveled to point B and stopped. If you measure the area covered by this trip here, known as A1, and you record that, then you allow the planet to travel, and then the planet will now you record the arc length from point C to D, then you cover this this all shaded region. Then again, you go to point E to F and you record the planet movement from point E to F, you will see that no matter where are we on the ellipse, the shaded region will be the same. So this triangle would cover the same shaded area, the same area compared to A2 compared to A1. So the time for little m, the planet, to go from point A to B is the same as the time it would take for it to go from C to D, as well as the time it would take for it to go from E to F, even though the triangles look like that, like one is bigger than the other, but that is not true. So the mass m moves fastest. So where is the speed of the planet rotating in this orbit the fastest? It moves the fastest when it is closest to the sun. And Kepler's second law was originally devised for planets orbiting the sun, but it has broader validity now. This is the Ptolemaic view. This is not true. This was a very old model of how planets have a rotation. And obviously you see that the Earth is the center of the world, which is the center of the universe, which is not true. This is what Copernicus came up with, and this is the most accurate. And this is the model where all the planets rotate around the sun because the sun has the biggest mass. Each planet obviously has some moons rotating around it because you see the sun represents the big bowling ball. Everybody's rotating around it. But these planets represent for us the billiard balls, and these are the marbles. So even though the planets are rotating around the sun, there are even more little marbles, little moons that are rotating around these planets who are themselves rotating around the sun. So the Ptolemaic model of the universe has the Earth at the center with the moon, and the planets and the sun and the stars revolving about it in a complex circular path. This is not true. So here the geocentric, meaning that Earth-centered model, which can be made progressively more accurate by adding more circles, is purely descriptive, containing no hints about causes of these motions. So Copernicus has a heliocentric, sun-centered model, which is a simpler and more accurate model. So what's the difference between geocentric model? Geocentric makes the Earth the center of the rotation of the sun and all of the other planets, which is not true because Earth is not bigger than the sun. That's like saying when you drop a bowling ball and those little billiard ball, the bowling ball is going to go around, and that is not true. That was an older geocentric point of view, but the Copernicus point of view is known as helio. Helio is like the helium gas. That is what the sun is made up of. So the heliocentric or sun-centered is the most accurate because the sun is the biggest. And there is other bigger bodies on which even the sun is rotating around those bigger, even bigger stars. So if we look at our ellipsoid orbit, we see that the major axis is the length of the ellipse. So here we have a major axis, and the major axis represents the length of the ellipse. So the ellipse looks like a curved, a egg-shaped rectangle. So it has a really long length and a shorter width, but they are perpendicular. So if you connect the two, if you make a center for this ellipsoid shape, this egg shape, you make a center and you go to the farthest point to the left of that center. And then you go to the rightmost point that is farthest from the center. And you connect the line. That is the very longest line. That's like the equator. That's like the line that is connected in the farthest 2 points horizontally. That is the major axis. From the name, major, really long. Major axis, really long. And then you have the minor axis that is shorter. So it is connecting the 2 points that are the shortest, and that's known as the minor axis. And both of them have to be at perpendicular or 90 degrees to each other. And then we have this very important plane, coordinate plane. So the major axis is the length of the ellipse, and the minor axis is the width of the ellipse. So the semi-major axis is half the major axis. So the semi-major axis is half the major axis, and the semi-minor axis is half the minor axis. So let's look at what we have here. Here we obviously know that the area of all of these triangles, the area of all of these triangles is the same, even though they don't look like they are equal, they actually are. And the time to go from A to B is equal to the time from C to D equal to the time from E to F. That does not mean the arc length is the same. Obviously, AB is longer than CD is longer than EF, but the time taken for them is obviously the same, but the distance is because the closer you are to the sun, the faster you will move. So so AB is closest to the sun. So the planet is going to move really fast from A to B. Then from C to D is going to move mediocre fast. But E to F is going to go really slow because it's really far away from the sun. And these are the two focus. A focus that is representing big M and a focus that is representing this point that is farther from our center.